All right. And so last time we introduced this concept of crystal field theory. We talked about how it explained two properties of these metal complexes, these transition metal complexes. The color of the transition metal complex, because it corresponds to that crystal field splitting energy. And you can use this wheel here. If you know the wavelength of absorption, you can determine what your observed color is. And we also talked about how it explained the magnetic properties of these complexes, including which really means how many unpaired electrons there are. We spent last time talking about these octahedral complexes. And so remember what this represents is that we have these five d orbitals in our free ion, right? Hold on a second, the dog's going crazy. All right. So if we have a free ion, so for example, something like, I don't know, the iron 2 ion, it has these d orbitals that are all at the same energy. But then all of a sudden it forms a complex, an octahedral complex, and we have splitting of these d orbitals into these different energies. Okay, so these ones, we don't have to know the name of them, but just to be good and fill it all in, these represent the different d orbitals here, right? And so this influenced how we were going to fill in these diagrams with the existing electrons, okay? And so we had gone over these octahedral complexes, and we'll spend some time at the end, octahedral, reviewing what we learned about these octahedral complexes. But we have two more that we have to introduce here, these other diagrams. The tetrahedral and the square planar. So these are two other geometries that your transition metal complexes can adopt. So the first one we'll talk about are the tetrahedrals. Okay, this is where you have 4 ligands. And what's sort of unique about a tetrahedral geometry is all those ligands are completely evenly spaced around that central ion. So all evenly spaced. And we saw sort of the layout on our constants page of what that's going to look like. Again, if we have a free ions, d orbitals, they're all at the same energy. For a tetrahedral complex, when they split, you're going to get 3 high energy and 2 of them low energy. And again, you don't need to know the identities of these, but just to be good and fill them in. Okay. And so just like before, we're going to be filling in this diagram with these electrons from our transition metal complex. With our octahedrals, we had to consider the ligand identity because some of our ligands are what we called high spin ligands and other ligands were called low spin ligands, and that influenced how we filled in our diagram. For the tetrahedrals, because those ligands are all evenly spaced and there's only 4 of them instead of 6 of them, this crystal field splitting energy is always small. So what that means is that tetrahedrals are always high spin complexes. And remember what it meant to be high spin is you half fill all orbitals first. So given a complex that's going to have a tetrahedral geometry, so let's just take something like FeNH3, 2. Right, so given this complex, again, if I'm just going to determine the magnetic properties of this complex, that means I need to figure out how many unpaired electrons it has. So the first thing I'm going to need to do is determine the oxidation state on that metal, right? Because that's going to help me figure out how many electrons it actually has. In this case, NH3 is a neutral ligand. And how would you know that? Because we have this table here of all of our different ligands, and it has the charges on these ligands, right? So this is going to be something that you will have on your constants page. For ammonia, water, and this carbonyl group here, those are neutral, so they don't have any charge associated with them. So that just means the charge on my complex is going to be the same as the charge on my metal ion. All right, that what we call the oxidation state. Going to my periodic table to figure out how many, we can get rid of all this, ignore that. Figure out how many electrons, the electron configuration rather, of this iron ion. So just to do this fast, iron metal would have an electron configuration of argon, followed by the 4s2, and then the 1, 2, 3, 4, 5, 6, 3d6 electrons. If I'm going to form the iron 2 ion, I'm going to need to take electrons away. So that leaves me with the configuration of argon and then just the 3d6. So I have to do this in order to determine how many electrons I have to fill in my diagram with. So going back, we'll say that iron is argon plus the 3d6. And so that means I'm going to fill in my diagram here with 6 electrons, but I'm going to fill it in this high spin manner, where I'm going to go through and half fill all orbitals first before going back and doubling up. So that's 1, 2, 3, 4, 5, 6. So in this case, this has 4 unpaired electrons. Okay, so octahedral complexes, we talked about how they could either be high spin or low spin, depending on the ligand's identity. For tetrahedrals, they are always high spin. Okay, so the first 2 steps of figuring out your oxidation number, figuring out how many electrons you have, those are the same. And you have your constants page that tells you how, whoops, that was this one here, how the splitting pattern works for these tetrahedral complexes. And then you just have to know that because it's a tetrahedral, you're going to fill it in that high spin manner. All right, so then the last one are square planar complexes. These also have these 4 ligands, but they are not uniformly distributed. Ran out of room. All right, they're kind of like bunched up around the very center of that coordination complex, or rather of the the complex. And because of that, you see actually a much larger splitting energy than you would with a tetrahedral. So again, if I have my 5 equivalent free ion d orbitals, those are going to split into now the splitting pattern. Oh, dang it, I was already on that same page. The splitting pattern for the square planar. Okay. So now we have 1, 2, 3, 4, 5. And again, it doesn't really matter what the names of these are, but just to be good. Okay. And for these square planar complexes, because those ligands are not uniformly distributed, the crystal field splitting energy is always large. So kind of the exact opposite of what we said for our tetrahedrals, where we said that they were always small. For square planar complexes, they're always large. So what does that mean? That means for square planars, they're going to always be low spin complexes. And remember, low spin means that you fully fill lower orbitals. Well, bummer. Before moving up. Okay, so then so now we've got like a little bit of a pickle here, which is how do we distinguish between square planars and tetrahedrals, because they both have 4 ligands. Well, it turns out that square planars like to have the same electron configuration, which is a D8 electron configuration. So if you see 4 ligands and it has a D8 electron configuration, it's square planar. If you see 4 ligands and it has any other electron configuration, then it's going to be tetrahedral. All right, so then just to finish this off with an example, let's do nickel. Okay, so this is our complex. I'm gonna leave myself a ton of room here. Let's see if I can squish. Again, I got to figure out my oxidation state of my ligand. Water's another neutral ligand, the oxidation state of my metal. Water's another neutral ligand, so this would just be nickel with a 2+ charge. Going back to our periodic table, then we have to figure out what the electron configuration for nickel is with this +2. Nickel all by itself is argon 4s2 3d8, because it's 1, 2, 3, 4, 5, 6, 7, 8 spaces over in the D block. So nickel with the +2 charge is going to be argon 3d8. And that D8, along with the 4 ligands, is what lets me know that this is definitely going to be a square planar complex. All right, so now I'm going to go back here. So this is argon 3d8. So I'm going to fill in my electron configuration diagram here, but I'm going to do so in this low spin manner, where I'm going to fully fill all lower energy orbitals before I move up. Right, so that's how I got those fully filled bottom orbitals. Then I moved up. That would be 6 electrons, 7, 8. So this leaves me with 0 unpaired electrons. All right, so both the square planar and tetrahedral are complexes with 4 ligands. Square planar has a very specific D8 electron configuration. Once you've determined your geometry, you're going to go to your constants page, pick out which one of these splitting diagrams you need, and then fill them in accordingly. right? So again, what we learned today is that these tetrahedrals are always high spin, and that these square planars are always low spin. And then just to review for our octahedrals, it could be either, depending on your ligand. We have some high spin ligands. So for octahedrals, you have to look at the ligands. We have high spin ligands. And we have low spin ligands. Right, so how you fill in your octahedral diagram is going to be dependent on the identity of your ligand. All right, so that actually does it for all the new content. So what we're going to do for the rest of the day here is just to go through some examples of all these different complexes here, sort of lay it out stepwise how we're going to get it. All right, how we're going to get our magnetic properties here. All right, so let's clean this up just like we would sort of have it. All right. We could take over this page. All right, so for the following, we're going to first determine the oxidation state of our transition metal. And we're going to determine the electron configuration of that ion. From there, we should be able to determine the geometry of the complex. Okay, and then finally, draw our complete complex electron configuration diagram. All right, so that's what we need to be able to do. Given a complex formula, we need to be able to determine all of these following things. All right, so I'm going to put down a few complexes. I'm going to let you guys work together. You should grab a periodic table if you have a textbook, or just open up Google or something like that. I mean, you just have to have a periodic table in front of you. I'm going to be switching screens and everything like that, but just to try to minimize it, everybody take a second to pull up a periodic table and have one in front of you. All right, so here are our four complexes that we're going to do. All right, and just we have this on our constants page, the page that I showed you with the list of ligands, but just to make life a little bit easier here, I'm going to put it on this screen. We have the bromo group has a -1 charge, water's neutral, ammonia's neutral, and the cyano group has a -1 charge. So step one is to determine the oxidation state of each one of the metals in these complexes. All right, so everybody take a minute for each one of these. Determine the oxidation state of the metal. All right, and when you get this first one, we'll do it as an eye clicker problem here. So when you get the oxidation state of iron in this hexacyanoferrate blank, because you're going to tell me what the oxidation number is, put it into your eye clicker here. And remember, you're determining by oxidation state. It's not just the charge on the complex, it's the charge on the metal ion, taking account for your ligand charge, right? This is the net charge that accounts for what the charge of the ligand and the metal ion are. All right, and so when we're determining the oxidation state, let's say that we have a complex, their metal ion and some number of ligands gives us this charge. The overall net charge is going to be the oxidation state of that ligand plus, or of that metal, plus the number of ligands times the charge on the ligand. That's going to end up giving us our overall net charge of the complex. So in this case with iron here, I didn't know my iron, but I know that I have 6 cyanide ligands, cyano-ligands, each with a charge of -1, and that sums up to -3. So what? -6 is going to give you -3. That's how I can determine that I must have the iron 3 ion. Right, the oxidation state of that iron is +3. All right, so I'm just going to kind of keep notes. So now we're going to determine the electron configuration of this ion. So again, take out your periodic table and tell me what the electron configuration of this iron 3 ion is going to be. All right, we'll do this as an eye clicker as well. So you can put it in that noble gas abbreviation. What's the electron configuration of the iron ion? All right, so this is something I get from the periodic table. Got to have a periodic table, unless you've got it memorized, in order to get the electron configuration. And specifically, one thing I have to really keep in mind since I'm doing the ions electron configuration is that electrons are removed from S first, then the d orbital. So in the case of iron 3, if I go to my periodic table, iron all by itself is the electron configuration for iron, followed by 4s2, and then 3d 1, 2, 3, 4, 5, 6. So the iron 3 ion will also have those same core electrons, but now I've lost these 2 s electrons, as well as 1 from my 3d orbital here. So that would be 3d5. And this is important because that's going to tell you how many electrons you're going to end up putting into your diagram. So 3d5. All right, so now we need to determine our complex's geometry here. All right, and so we're going to do another iClicker for this one. We'll make it multiple choice. We got 3 options. We're going to say A is an octahedral, B is a tetrahedral, and C is a square planar. So given our formula, was Fe, whoops, Cn6 minus 3. We got to determine whether we have an octahedral geometry, and I guess we had our electron configuration too. What's it going to be? A, B, or C for our geometry? All right, this one's kind of a mixed bag. Remember, you got to look at 2 things. The first thing you're going to look at is how many ligands there are, because tetrahedral, in terms of number of ligands, tetrahedrals and square planars each have 4, but octahedral is the only geometry that's going to accommodate 6 ligands. So I'm going to have an octahedral geometry for this particular complex here because there are 6 ligands. Okay, I mean, just to sort of rewind back, this was sort of what we started out the day with on, what was it, Monday, right? So in terms of number of ligands, octahedral is the only one that has 6. Tetrahedral and square planar have 4. Notice that we're kind of conveniently skipping over these linear ones here. They're fairly rare. So we're going to stick to only these 3 examples when it comes to sort of drawing our diagrams. All right, and actually going back to this page, because now we've determined that this is an octahedral. All right, so in determining complex geometry, it's the number of ligands. And then if there's 4 of them, then we have to distinguish between tetrahedral and square planar by looking at the actual electron configuration. And that's because square planar is D8. Right, but in this case, I have 6, so I know I'm going to need that octahedral geometry. All right, so then just to sort of make some room for myself, in order to now complete my electron configuration diagram, I'm going to first copy down the one for, let me get rid of it, make that tiny. Copy down the one for an octahedral. Right, so my octahedral geometry leads to this sort of a splitting pattern. So I'll just actually copy and paste this thing over. Okay, so that's my octahedral diagram. So in order to complete the electron configuration diagram, I'm going to grab the diagram for the specific geometry. And then I got to determine high spin or low spin, because that's going to influence how I fill in this diagram here. And specifically for octahedrals, it's going to depend on the ligand. So I got to go to my table and see where the cyanoligand falls on my electrochemical series. This is the one with the largest splitting energy, meaning it's a low spin complex. Right, so then when I go back here, I know I have 5 electrons to fill in this diagram, and I'm going to fill it in a low spin way where I fully fill low energy orbitals first. So I'm going to go through and fill in such a way where I'm going to fill my lower energy ones, and before moving up to the next energy level, I'm going to fully fill these bottom ones first. And in this case, I run out of electrons at 5. So this is my complete diagram for this particular complex. All right, so that's the process we're going to have to go through for each of these here. Determine the oxidation state of the metal. Figure out your electron configuration so you know how many electrons you have to work with. Determine your geometry so you know what splitting pattern you're going to see. And then finally fill it in with those electrons, considering whether the complex is going to be high spin or low spin. All right, so for the sake of completeness, I'm going to work through these here. These are something that ideally you can do on your own at this point. Oops, I messed that up. Try to get as much room as I can here. All right, so for the sake of completion, I'm going to work through it here. If you think you sort of know what you're doing, you can go ahead and like mute or something like that, and then just like check up at the screen as you're moving along to make sure that we're getting the same answer. Because again, ideally, you can do these all on your own here, especially now that we've laid out this process. All right, so water is a neutral ligand, so that just means that my charge is going to be the same as what it is in the complex, +3. If I go to my periodic table, copper all by itself is argon 4s2, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. So then if I have the copper 3 ion, I'm going to lose both of these 4s electrons as well as one from the 3d, giving me argon 3d8. Now I have to determine my complex geometry. This is a complex that has 4 ligands, which means that it's either tetrahedral or square planar. But the fact that it's 3d8 lets me know that it's going to be square planar. I'll say for this one, it was a low spin ligand. That's how I know. Okay. So square planar, I'm going to go and grab my square planar diagram to get rid of all this noise. It's this one here. Okay. And now I have to fill it in. For square planars, they are always low spin. So again, I'm going to fully fill those lower energy orbitals first before moving up. So I have 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. So that's my my electron configuration diagram for that particular complex. So the only number of ligands that you're going to get are going to be correspond to those values of either 6 or 4. Again, there are sometimes complexes with 2, but we sort of haven't done a crystal field theory on those linear complexes. So the only ones that we're going to see are going to fall into one of those 3 bins: octahedral, tetrahedral, or square planar. All right, so for this one, chromium, again, I got to determine the oxidation state on that chromium. Although I messed this one up, sorry. I'm going to change this example a little bit. This should have been 4 ligands. Otherwise, it doesn't prove the point that I'm trying to here. So still doesn't change the oxidation state on that chromium is +2 because my ammonia is a neutral ligand. All right, so then my chromium 2 electron configuration for chromium all by itself is argon 4s2 3d4. For the chromium 2 ion, we got argon and then just the 3d4. So now in terms of the geometry at this step here, I'm going to look at the number of ligands. There are 4 of them. So it's either square planar or tetrahedral, but my configuration is 3d4 and not 3d8. So this will be a tetrahedral. And tetrahedrals, in contrast to square planars, are always high spin, meaning we're going to half fill all orbitals before doubling up. So if I grab my tetrahedral diagram, I'm going to fill it in this high spin manner where I'm going to go through and half fill all of these orbitals before going back and doubling up. So that would be 1, 2, 3, 4. And that'd be it. That's my electron configuration for this tetrahedral complex, the tetramine chromium 2. All right, and then my last one here, I got to determine the oxidation state on the iron. Bromo groups have a -1 charge, so I'm going to have to do some math, just like I did in my first example, to figure out what the oxidation state is. I have 6 of them. Each of those 6 have a -1 charge, and the sum is that positive or that -3 charge, meaning that my, whoa, what did I even do? Okay, meaning that my charge on my iron ion has to be +3. All right, and now going to my periodic table, I got to figure out the electron configuration for that iron ion. Iron all by itself has an electron configuration of argon 4s2, 2, 3, 4, 5, 6. So then my iron 3 ion has the same core electrons as argon, but now I've gotten rid of that 4s electrons and 1 from the 3d, so I'm left with 3d5. Oh, it's not here. So this is argon 3d5. I have to determine my geometry. And since there are 6 ligands, there's only one choice, which is that octahedral geometry. And since this is an octahedral, I know what diagram I'm going to grab. So we can just do that real quick. I'm going to grab this octahedral diagram. Paste that over here. Okay. But I got to determine how I'm going to fill in this diagram. And for octahedrals, it depends on the identity of the ligand. So I'm going to have to go back to my series here, and I'll see that bromine is on the low end of my spectrochemical series. So it is a high spin ligand. So that means I'm going to fill in this diagram in a high spin way. We have a high spin ligand, which means just like we saw with our tetrahedral, which was also high spin, we're going to half fill all orbitals before starting to go back and double up. And so in this case, filling in this diagram here with 5 electrons, I'm going to go 1, 2, 3, 4, 5, half filling all orbitals first before going back and doubling up. All right, and I specifically chose these 2 examples because they have the same iron 3 complex or iron 3 ion. The difference is the ligand, and that one of them is low spin, leading to this filling pattern here, whereas the other one is high spin, leading to this filling pattern here. All right, so this is what we learned last time for those octahedrals. I guess my D disappeared. For those octahedrals, you have to pay attention to what your ligand is, and that will tell you how you're supposed to be filling in these diagrams. For the 2 that we learned about today, square planars are just always low spin, and tetrahedrals are always high spin. All right, so these are how we determine the magnetic properties of these transition metal complexes. And these are like the 4 possibilities that we have here. Again, you need to go through this process. You got to know what the oxidation state on the metal is, because that'll help you figure out what your electron configuration is. and you need that electron configuration in order to determine how many electrons you actually have. Then once you determine your geometry of your complex, you're going to take those electrons and use it to fill in those diagrams that we have on our constants page, considering whether you should be filling them in a low spin manner or a high spin manner. All right, so that closes it out for chapter 26. Again, we have our review day on Friday where we're just going to rewind back to chapter 17 and try to fit in as much content as possible. And then after that, we will have our exam that next week.